Today we study C18, gradient and differential area volume element. Okay, this file can be downloaded from kpop.org. If you scroll down, you'll find all the way down to find Escape from Scientific Absurdity, Series A, B, and then we have Escape from Scientific Absurdities, Series C. And this file can be found at C18. Click here to find the PDF file. And then click here to find the YouTube Korean version. 오늘은 C18. And after completing this lecture, let me upload this English version. Now it is empty. And if you visit youtube.com at Kpop, you will find various playlists, and our lecture will be uploaded in the Escape from Scientific Absurdity, and there are so many, all of the series A, B, and C, everything. Okay, let's begin with the C18. First, we consider gradient operator. Gradient operator is a vector operator. Usually it is applied to a scalar function. And actually in physics we say scalar field. Field means it is a function of a position vector. So a position vector can be expressed in the Cartesian coordinate system. 3 coordinates x, y, and z. As it is. The differential operator that is attached to the unit Cartesian basis vectors are partial differential operators. This means partial differential operation with respect to x. Here x1 represents x, x2 y, and x3 z. 3 Cartesian coordinates. If I take the derivative with respect to x, I keep y and z the same. So, by definition, it's a derivative, partial derivative with respect to x varies the argument of x only and take the ratio of the differential of the function divided by the shift in the argument. The same is true for the y and z derivative. Y and z derivative. As an example, I can take the x derivative of this function. Now y and z are treated to be constant factors. Therefore, I can pull it out. The derivative of x with respect to x is 1. Hence, the result is y squared z squared. If I have x squared yz, I can pull this yz out, and derivative of this is 2x. The final result is this. If the function does not have any x dependence, then it is simply vanish. Let us consider the 3D plot of some operation applied to this scalar function defined in 2-dimensional Euclidean space. If I draw a three-dimensional plot, this is x and y, and z is value of f evaluated at x comma y. So x vector is x e1 hat, y e2 hat. Sorry. So this plot shows the function f has a maximum at this point somewhere and has the minimum somewhere. Okay, this is the point at which this function has the minimum. This is the point at which this function has the maximum. We find this function increases, decreases, decreases, increases. Okay. The plot in the middle shows the contour of this function. Contour means you give me a number whose value is a certain value, then we can cut the figure. Then you will find a closed path having the constant c, f equals some constant. So this one is called contour. So the direction of maximally increasing this function is the steepest path that is perpendicular to this contour. Okay? Near here, function increases in the steepest way, and the other way, the slope decreases in the steepest way. What is this figure? Okay, these 2 points, let us call A and B, and this is A, and this is B. We know this function decreases as we go far away from this point B, but this arrow shows the direction of a decreasing function of f. So gradient of f is represents the steepest direction of increasing this function. Therefore, it is opposite direction. I guess this is minus gradient of f. So this is a gradient is a vector field, and gradient of a scalar field represents a direction of maximally increasing the scalar field. Minus the gradient of f represents the maximally decreasing direction, and the magnitude is the slope of decrease. Okay, these are the answer. Contour plot represents a curve satisfying a constant value of this multivariable function. This multivariable is assumed to be defined in the two-dimensional Euclidean space because the operator, gradient operator, evaluates the slope along a certain direction. Gradient of a scalar function f and minus gradient of a scalar function f, they are opposite. So usually if f is u, potential energy, minus the gradient of potential energy of a conservative force, that is that conservative force f. Let us consider a point on a circle of radius r centered at the origin. This is the circle of radius r, and we would like to introduce a differential radius, and we would like to introduce a differential angle d theta. Okay. First of all, two-dimensional position vector can be represented by a Cartesian unit vector, linear combination of Cartesian unit vector. And if I use polar coordinates, its vector, radius vector, position vector, can be represented by the radius multiplied by unit radial vector. We also have another basis vector on the two-dimensional plane. If I introduce the polar coordinates, we have the direction that is tangent to the radius, and we use this one as E theta that is perpendicular to this, so I can cross the Cartesian components and flip the sign on the front term. This is the unit tangent vector. This is the direction E theta minus, that is the direction of decreasing angle. This is the direction of E theta hat, that is the direction of increasing angle. And this is unit radial vector. They are perpendicular to each other. If I vary R only, then the variation will give the dr E r hat. That is the unit, that is the radial displacement, infinitesimal radial displacement. And infinitesimal tangential displacement is multiplied by E theta. Let's see how to compute this. Find the differential displacement vector. First, I'd like to find out the change in the position vector by varying radius like this, but keeping theta constant. In principle, a function total differential in the polar coordinates should be expressed as a linear combination of the two differentials. But if I keep theta constant, this one disappears. If I keep radius constant, this one disappears. In such a manner, I can compute the differential displacement vector by varying R only and keeping theta the same. We substitute this x in here and apply Leibniz rule. We know this unit radial vector is independent of R. Therefore, I can pull this vector out. The partial derivative of R with respect to R is nothing but the unity. The answer is this. From here, we can say ER equals x divided dr multiplied by dr. That's it. Next, we consider change in the position, that is displacement, due to the variation of a theta, keeping R fixed. In a similar manner, I can say x equals RER hat, and there is no theta dependence in the radius. Radius is pulled out. So if I pull the radius out, I take the derivative with respect to theta. This one becomes minus sine theta, and this one becomes a cosine theta. So if I multiply E1, E2 and add them up, this is nothing but the unit tangential vector that is perpendicular to the unit radius vector, radial vector. From here, I can conclude that E theta equals 1 over R partial derivative of x with respect to the angle. Okay? Now, we evaluate the scalar product between ER and E theta. And the scalar product gives only 1, 1, 2, 2. And we know E1 dot E2 equals 0 because they are perpendicular to each other. So we only consider this scalar product and this scalar product. This is a minus cosine sine, and this is sine sine. They sine cosine. They cancel exactly. This means the ER and E theta, they are perpendicular to each other. In addition, we will find that the cross product of ER and E theta is E3. Let's see. ER, E theta. We know the multiplication table. They same thing. They are all 0. 1, 2. They are anti-commutative. Minus 2 cross 1, and that is E3. So we substitute this multiplication table to find the cross product of ER and E theta. So final result is surviving terms are cosine squared and sine squared with negative sign. But we know these two are identical to each other. So we can factor E3 out and apply Pythagoras' theorem to find that ER cross E theta equals E3. As a result, differential area element due to the variation of the R, that is ER hat, and E theta, we have these two side vectors for a parallelogram. The area of a parallelogram can be computed by applying area vector, the cross product of the differential displacement vector. That is this is this. We find that ER cross E theta equals E3. As a result, we obtain this. Finally, if I take the scalar product with the E3, then we arrive at the area itself. That is RdR d theta. Why don't we integrate over the variable r runs from 0 to capital R, the radius of the whole circle, by varying small r to 0 to capital R. And we integrate over theta that runs from 0 to 2 pi using the area element, and here we can carry out the two integrals. They are trivial. Finally, we arrive at the radial integral and angular integral. The result is pi r squared. Why don't we extend this idea to evaluate the volume of a sphere? A sphere of a radius capital R is introduced in here. A point on a sphere can be parameterized by introducing the polar angle theta. If I have a radius r, the perpendicular distance and the perpendicular distance to this z-axis should be r sine theta, and the distance from the origin to this point is r cosine theta. Because this radius, planar radius, is r sine theta, if I introduce x and y coordinate, then it's a projection. It's a projection onto x-axis is r sine theta cosine phi, and projection onto y-axis, this one is r sine theta sine phi. We know theta runs from 0 to pi and phi runs from 0 to 2 pi. So polar angle, azimuthal angle, that runs from 0 to 2 pi. Now we are ready to express a point inside a sphere of radius r. That means this radius small r should be equal or less than the radius r, capital R, of the sphere. We know how to represent a point inside a sphere whose radius is a small r, and we use unit radial vector that we just have found. Z component is cosine, x component is sine theta cosine phi, y component is a sine theta sine phi. Using this relation, I can find a unit, the displacement vector along the radius, displacement vector along the angle, polar angle theta, and azimuthal angle. Let's do it by varying the radius only, and we use this formula. We have this result. We know this is independent of radius, so the final result is immediately obtained. So ER hat is the partial derivative of position vector That's it. Why don't we compute the displacement due to the variation of polar angle? We have this. Now radius is factored out. However, ER has a theta dependence. Theta dependence appears here, here, and here. After taking the partial derivative with respect to theta, we have cosine, cosine, and minus sign. As a result, what we have obtained is E theta. Using this relation, 1 over r x partial derivative with respect to the polar angle. Finally, the displacement along the azimuthal direction can be obtained by replacing x with r e to the r. And I have factored this out, and we take the derivative with respect to phi and multiply the differential over phi. Because ER is given in here, and phi dependence appears only here and there, the last term vanishes. And this is a constant coefficient. They are common. I factor this out as r sine theta, and the remaining factor represents E phi. We know from this relation, E phi can be directly computed as 1 over r sine theta. Okay, so finally, we arrived at the point to compute the differential volume element due to the variation of radius, polar angle, and azimuthal angle. We bring these results all together here, here, and here. We have this result. The radius, small r, runs from 0 to capital R. Polar angle runs from 0 to pi. And azimuthal angle runs from 0 to 2 pi. The volume of a sphere can be evaluated by integrating over the allowed region, and these are all trivial integrals. The first one is 1/3 RQ. The second one can be expressed as 1 at angle theta equals 0, cosine theta is +1. At pi, it is -1. So it is integral -1. This minus sign is absorbed by exchanging the upper limit and lower limit. And this trivial integral is 1 minus -1, and that is 2. And the azimuthal angle integral is also trivial. Finally, we arrive at 4 pi third r cubed. We can also evaluate the center of mass of this sphere of radius capital R centered at the origin by making use of the definition of the center of mass. And we know how to parameterize the position vector in terms of polar coordinates. Using polar coordinates and by making use of the differential volume element and applying the uniform density of the mass distribution over a sphere, we arrive at this. First of all, phi azimuthal angle dependence appears here and there, and this is evaluated over a period of a sinusoidal function that cancel exactly. Then it is 2 pi for the third term, and what we find here is something like this. This is evaluated -a to a f odd x dx. Any odd function evaluated over any odd function, they are opposite, plus and minus, from -a to a. This integral vanishes. Therefore, the center of mass of a uniform sphere centered at the origin is the origin itself. It's at 0. That's it for today. Thank you.